Buenas tardes con todos y todas. Agradecemos su participación en el inicio de esta nueva serie de webinars, la cual será desarrollada mensualmente y es a su vez coorganizada con 3 universidades nacionales. Damos así inicio a esta serie de webinars con la ponencia del Dr. Parson. Aprovechamos también en saludar a nuestro comité conformado por el Dr. Goicoechea de la Universidad Nacional del Niño Valdizán de Huánuco, el Dr. Adán Solórzano de la Universidad Nacional San Antonio Abad del Cusco y el Dr. Alberto García de la Universidad Nacional de la Amazonía de Iquitos, Loreto. Reyaco es una plataforma educativa en Latinoamérica que busca descentralizar el conocimiento y generar investigación en temas de agua y medio ambiente. A través de esta iniciativa, fomentamos la combinación de ingeniería, ciencia y tecnología para el desarrollo de soluciones ambientales. De esta manera, buscamos promover la conservación de los ecosistemas y el desarrollo de la infraestructura sostenible a través de la mejora en la toma de decisiones. En esta oportunidad, el webinar titulado The Evolution of Flood Hazard and Risk in the Changing World presentará la evolución de las medidas y desafíos frente al riesgo de inundaciones, considerando la importancia de tener una visión integral de cuenca y la interacción con la sociedad en la capacidad adaptativa de las ciudades. Esta ponencia es brindada por el Dr. Daniel Parsons, profesor en sedimentología y director del Instituto de Ambiente y Energía de la Universidad de Hull en Reino Unido. El Dr. Parsons obtuvo su doctorado en la Universidad de Sheffield, Reino Unido, y su investigación se enfoca en el estudio de perturbaciones antropogénicas en ambientes sedimentarios fluviales, estuarinos y costeros, explorando de esta manera las respuestas de estos sistemas al cambio climático y ambiental, así como las adaptaciones sociales necesarias para mitigar los impactos. Asimismo, el Dr. Parsons ha trabajado en el desarrollo de modelos ambientales y en tecnologías innovadoras para medición ambiental y áreas relacionadas con la energía renovable en alta mar. Quiero mencionar que este evento está siendo transmitido vía Zoom y en Facebook, así como también en los canales de las universidades coorganizadoras. A quienes nos siguen en nuestros otros canales, por favor, les pedimos que nos hagan llegar sus preguntas y comentarios al término de la ponencia, o también utilizando la sección de preguntas y respuestas de la plataforma Zoom. Recuerden que los que están conectados también en la plataforma Zoom pueden hacer uso de la traducción simultánea de inglés a español en cualquier momento haciendo clic en el botón de interpretación en el menú inferior de su pantalla. Many thanks, Dr. Parsons, for giving us your keynote lecture. It's a pleasure to have you here, and I'm pretty sure we will learn a lot today. I know everybody's waiting for you, so please go ahead.
Gracias. And yes, I'm looking forward to presenting the seminar today. Here in England, it's 10 p.m. so rather late, but I know it's a better hour for seminars where you are. I'll go ahead here and share my screen. Hopefully you can now see that. I think that's working properly. So yes, so I want to tell you about some work myself and colleagues have been doing on trying to understand how flood hazard and risk change through time and space. And I'll present to you a new project that we've just had funded. And we'll talk through that project, what our aims are, what we're investigating, and give you some insight into some of the things that we have, some of the progress that we have made in those pieces of work so far. I'll then delve into the background, into some of the issues and some of the questions or outstanding questions we have around how flood hazard and risk changes over time and space, and some of the controls on how flood hazard and risk changes as well. And I'll particularly focus on some recent work that we've been undertaking here at the University of Hull, looking at scaling the impact of vegetation and changes in vegetation on morphodynamics, and how those morphodynamics then play a role in terms of that flood hazard and risk. And alongside that, as I work through the examples and some of the previous work that I've been involved with, I'll also delve back into how we assess changes in flood hazard and risk over longer periods of time, and how we can use the sedimentary record to do that, and try to recover paleo flood records, and perhaps test some of the assumptions that we have in some of the scaling relationships that we use when interpreting the rock record. So hope that gives you a little flavour of the structure of the talk and the journey I want to take you on over the next short period with me here. So first of all, I want to recognise a whole range of people. I want to thank you all, obviously, for coming along. Thank Jorge Abad for the introduction to the series and inviting me to speak today. But I also want to thank a whole range of co-workers as well, and I'll name check those as I go through the presentation today, in terms of the contributions that others have made to the work that I will present. So to start with, the evolution of flood hazard and risk and how that changes across the globe is something that we've been focusing on as a team for a number of years now. And I was delighted late last year to finally, it's been a while coming. We've tried, and hopefully this is a good example of where we've tried to obtain funding for this big project a couple of times and just missed out. And but we resubmitted it and persevered, and we got a Natural Environment Research Council large grant. It's a £3.7 million programme, so the biggest grants, biggest projects that the council in the UK fund. And it's called Evo Flood. Involves a whole range of colleagues from these institutions here, and myself and Steve Darby in Southampton are leading the programme with a whole range of colleagues across the UK and internationally as well. And really what we're trying to do here is understand how flood hazard changes over time and space, and that's important because each and every year, about 300 million people across the globe are impacted by floods in some way. And what we were trying to do with what we're attempting to do with this project is understand how the controls on that and how that changes over time. And of course, even outline projections suggest that with climate change, that flood risk is set to at least double by 2050. So, the cost of flooding, both in lives and livelihoods, is very real, and we need to understand how those changes will result in that changing risk and vulnerability into the future. Of course, flooding not only affects lives and livelihoods, it also has a devastating impact on infrastructure as well. And some recent major flood events costing billions of dollars in flood damages. And again, that even outline projections again suggest that these sorts of impacts to infrastructure and critical infrastructure as well are set to increase into the future as well. So having a handle on the vulnerability of our infrastructure around the world is also a key driver for the work that we're pioneering as a result of this project. And of course, in many parts of the world, flooding on the ground looks like this. I mentioned the 300 million people that are impacted each year. And to put that into perspective, that's the entire population of something like the United States of America. So it's a massive amount of people that are impacted. And in many parts of the world, flooding on the ground looks like this. It does take lives and it does devastate livelihoods as well. So there's a very real need in terms of emergency planning, in terms of response, and in terms of reducing the impact of flooding when it does happen on populations. There are key drivers in doing all of that. Now, our ability to model flooding is actually improved significantly over the past 20 years. Here I'm showing you some inundation extents maps from the list flood modeling package for different rivers around the world. And you can see that, with a relatively high degree of fidelity, we're able to here predict the 1 in 100 year flood event for each of these systems, and we can test the skill of the model and compare it to Earth observation data, and it does a reasonable job of mapping the extents to a general pattern relatively well. But we know that these sorts of models, these sorts of what we term global flood models, are fundamentally flawed in terms of the assumptions that they take on. And that's because we ignore or we misrepresent a whole range of factors that we know are really important when we're looking at these flood models. The way in which the models currently compute inundation and overbank discharges they're essentially fixed pipes. They don't change over time, and there's no morphological conditioning in any of them. They just convey the water that's supplied to them from the hydroclimate. So that channel conveyance capacity and how that may change through time and space isn't really captured within these models in any real way. The way in which the floodplain and the channel connect together as well are also very simply represented within these models, and how that changes in time and space is also poorly represented. The models additionally have very simple treatments of roughness, and we know how important roughness can be as a parameter within these models, how floodplain roughness and channel roughness can be very different over relatively short distances, and at the moment uniform roughness tends to be applied, and we know that that's a big limitation on how well the models capture a range of important flow transfer processes. Most of these models don't include dams or damming or the impact of dams, and we know how important that is for the conveyance of flood. And when we look at river network and type and different types of channels, multi-threaded channels, wetlands, and the impacts of some of those features, again, very simple treatments of those are used at the moment. And then finally, when we start thinking about how flood hazard transitioned into flood risk, particularly when we're looking into the future, we don't take any account of the dynamic nature of populations across the globe. So we don't factor in where people will be living in the future as a result of the expansions of some big cities, big urban conurbations, and we don't incorporate any of this dynamic population modeling that lots of groups are doing around the world. We don't couple that in to any of our flood models, and as a result we are not only simulating static landscapes when we're thinking about flooding in the future, we're also simulating static populations as well, and clearly that's a fundamental limitation on modeling flood hazard into the future. So EvoFlood, the project, is really set at addressing these limitations and beginning to quantify the impacts that they may have. And we know we need to do that because lots of recent work, so this is some of Louise Slater's work published a few years ago, and Louise is part of the project team, where she was able to demonstrate using records across the US how it's not just hydroclimate that controls river channel flooding. And what she was able to show here is actually channel change effects, the impact of morphodynamics, and what role that can play in flood hazard, and she was able to demonstrate the geographical controls of some of this as well. So what you're looking at here on the right hand side with this map is a set of hydroclimate driven effects on the top, and channel change driven effects at the bottom. And what they're showing is what are the first order controls on channel conveyance. So what's controlling the ability of those channels to convey the floods that are supplied to them? Is it the hydroclimate, so changes in hydroclimate, or is it changes in geomorphology, changes in the channel shape over time? And of course, as you change the channel shape, so if you grade the bed, if you shrink the channel, then you can convey less flow in terms of that cross-sectional discharge. And Louise's work was able to demonstrate how that becomes a first order control in many locations, and up to around 30-40% of the cases, it was actually channel change that was more important than the hydroclimate. So it kind of puts into perspective the modelling that we undertake at the moment that assumes these static pipes that don't change over time. We know rivers do change. We know that they move, they migrate, they change their shape, and we have to incorporate those sorts of predictive models when we're looking at flood evolution over longer periods of time. And some of the really neat modeling that this is some Earth observation data and some I'll just play this Earth observation data, and then at the bottom there's some models, the H-star model that Andrew Nicholas has developed in Exeter University, and you can see that both from the Earth observation data from a river, the some of you may have worked on, and also the Brahmaputra in Bangladesh, you can see the dynamism of these channels and how that morphodynamics is really integral in terms of how they change over time. But you can also see on the bottom, if I replay this, you can also see how these channels, how the model is able to capture lots of these dynamics. So this is a two-dimensional morphodynamic code that is able to reasonably well replicate both single thread and multi-thread channels in the same framework, which is a major step forward in a range of different types of modeling efforts, and we can capture the sorts of morphodynamics that we know is perhaps important when we start thinking about flood conveyance. So not only do we have the modeling tools in terms of the list flood engine and those global flood models, we've also got Earth observation data sets and modeling tools now available that we can start to capture some of these dynamics and think about how we integrate them into our longer term flood modeling. So the EvoFlood program is going to do exactly that, and I'll show you an example where we've started to do that in a minute. But I just want to explain the approach first of all. We could take the H-star morphodynamic modeling code and run a suite of scenarios to look at how changes in discharge, changes in sediment supply into these reaches of channel impact the morphodynamics, and how the morphodynamics impact the flood conveyance. So we can work out for different bank heights and different types of parameter sets, ways in which we capture conveyance change due to different parameter sets, perhaps provided by the basin. From that type of modeling and looking at different types of land use change, or perhaps looking at different hydroclimate impacts on basin discharge or on basin sediment supply, we can run the H-star model with a range of scenarios and look at the sorts of behaviors that we see within the modeling framework. From that, we're able to work out and work out a set of parameters, a kind of lookup table, if you like, that would provide a 1D channel evolution model, and we can apply that to all river basins across the world. So once we've done that, we would have a channel evolution model that would capture the morphodynamic effects on channel conveyance capacities. So a very cascade of models that would provide just that nodal point relation between channel evolution and channel conveyance capacity based on those parameters provided. We can plug that into global river networks and then plug that into global flood models. So what we end up with is a dynamic way of capturing morphodynamic driven channel conveyance change. So when we then run the the global flood models, we're able to incorporate those morphodynamics and the way in which those morphodynamics impact channel conveyance capacity globally and how that changes over time as well. So we transition a global flood model from being something that is statically modeling changing hydroclimate to incorporating how the morphodynamics respond in time and space as well. So that's the essence of what we're trying to achieve with the Evo Flood program, and of course we'll be validating those approaches using Earth observation data sets, some historic data sets in terms of paleo flood changes, and also using laboratory models. And I'll say a little bit about the laboratory models later on to validate some of the work. Now, we've run a proof of concept of this, and I'd like to talk you through that and demonstrate how this can couple together and provide a really great way to pull out some of the really big scale and large scale impacts that incorporating these sorts of effects can have. So our test case was to run the global flood model on a much smaller scale. So we took the island of Taiwan, and I don't know how many of you know Taiwan well, but we have the west side of Taiwan is heavily populated lowland coastal plain with large elevations to the east that drain a range of significant river basins. I mean, you can see the sorts of, the numbers of people that live on this coastal plain that we've zoomed into here. And what we've run is a global flood model with a 1 in 50 reoccurrence flood interval applied, and looked at the populations that were exposed to that 50-year flood event, and you can see the sorts of areas that become inundated with a 50-year flood in terms of the areas impacted. So that gives you a baseline kind of understanding of the potential impacts on the population. If we grade all of the riverbeds by 3 meters, and that might sound a lot, but with some of the large scale earthquakes and some of the big impacts of things like the typhoons that come across the island, those sorts of numbers are actually relatively conservative. Some of these river channels. There was when Typhoon Morakot came across Taiwan. Some of these riverbeds were observed to a grade by 5 meters during a few of the events. So it's a relatively high number, but conservative within the numbers that have been observed over the historical record. So we put a 3 meter aggradation everywhere. So that is an assumption, but this is a test just to demonstrate the proof of concept. But as a result of that 3 meter aggradation, and when we rerun exactly the same hydroclimate, so the 50-year flood event, the 50-year reoccurrence flood event, an additional 1.5 million people are exposed to that flood. So it begins to demonstrate how important the morphodynamics, the conveyance capacity of the channel is to the number of people that are exposed from a given flood event. And we can start comparing some of these, and the table here shows you the 50-year flood and the 100-year RI flood, and we can look at a 1 meter, a 3 meter, or a 5 meter bed aggradation across the coastal plain, and you can see the impact that this has, practically doubling, then maybe tripling the number of people that are impacted by the flood events just by incorporating some of the morphodynamic impacts on the river channels themselves. And you can see the extra areas that are flooded by incorporating this. Relatively simple assumption, but a nice proof of concept that demonstrates how important in terms of moving from flood hazard to flood risk, incorporating the morphodynamics can be. So the questions that we'll be addressing within EvoFlood are listed here. I'm not going to read them all out here, but I'll talk around out them and leave them there for you to read through as I'm talking. But what we're really interested in is understanding how flood hazard and risk, the frequency of flooding changes as a result of that morphodynamics, how bankful flow changes as a result, and the impact that has on probability. What drives that? So is it land use? Is it hydroclimate itself liberating more sediment from the hinterland? What's the main drivers on the changes that you see, and how does that vary globally across different biomes, across different parts of the world in terms of the impacts of climate change? How important is this in permafrost environments, for example, where perhaps more sediment is going to be liberated and with non-linear relationships? Which areas are more sensitive than others? I mentioned permafrost, but perhaps ephemeral systems become more prone to these impacts, and how they change through time. How do changes in sediment supply that result from them change that flood conveyance? What does that do to floodplain connectivities, for example? And we know how important that can be for flood inundation and extents. Where in the world is morphodynamics more important than hydroclimate, and vice versa? And that's a first order question that we really want to answer, to really map out the vulnerability of different systems to these different effects. And where does one perhaps amplify the other would be another way of thinking that, and what the time scales that they work over. So if you have a changed hydroclimate, how long does the morphodynamics take to respond to that changed hydroclimate and the river adjust to the new regime? What's the trade-off there, and what's the interactions? And then finally, how does flood risk and vulnerability overlay in that, and how does the changing populations globally and the predictions around those, where's the big intersections there? Where are most systems at risk, and how do they line up in terms of risk mapping? So they're the sorts of questions that we really want to delve into, and I want to really kind of now go into some of the background that provided some of the thinking that drove this project, and give you again some examples of the work that we've done leading up to this. And lots of that came from, excuse me 1 minute. Lots of that came from trying to understand what variability, what impact variability has on river channels. So does that variability, so changing regime, changing flashiness, let's say, of a river basin, changing flood durations, what does that hydrological flow variability do, and how does that change the way in which a river system works? Lots of work we've done in river science tends to focus on regime, or tends to focus on the equilibrium condition. But how important is variability within that, the extreme events? How important are those, and where does that matter? How do changes in sediment availability impact that? So this hysteresis between flow and sediment availability and sediment discharge. So where and how is that important? When we see the kind of changes in morphodynamics, where that's either extrinsically driven or intrinsically driven, what's the controls there, and how important can they be? What impact does shocks or perturbations to systems, so the really big 1 in 1,000 year flood event, how does that really impact? Does that reset systems? Are there tipping points in the way that these systems and river systems respond to that variation? And ultimately, I guess what we're trying to capture here is the morphology that we measure quite often, and is the sedimentology, when we're thinking about the paleo record, a really good, reliable measure of the morphodynamics of the system. So I'll repeat that because I think this is a really important point. So is morphology a reliable measure of morphodynamics? So if we go out into a river system and measure the morphology, can we really say anything about the morphodynamics? Or do we need more information to understand the morphodynamics because of the variability within the system? And ultimately, I guess the kind of question, all of these questions boil down to: does unsteadiness matter? Does transience matter? Does variability matter in a river system, or is a steady state equilibrium condition the thing that we really need to kind of understand? And I guess the pushback or the argument from that, from my perspective, would be we probably do need to understand what this kind of change means over longer periods of time, for sure, and changes in variability over longer periods of time, because we know that the climate is changing as a result of global heating, and we need to understand what either long-term trends change or changes in variability as a result of climate change, how our systems will respond. And I think we need to delve into that question, because some of the things that I'll show you just now will perhaps point to how important some of these things really are. So that attests to the last point here, is how do we make those longer term predictions if we don't understand variability and long term trends on the driving parameters of these systems, particularly when we know non-stationarity, i.e. climate change, is already having an impact on some of these. So I want to focus on discharge variability first. We know that when we're looking at discharge variability, that we see changes in the morphodynamics of the system, but what does that mean in terms of the paleo environment, and how the sediments are laid down by these systems? And of course, there's a whole group of sedimentologists out there that will look at these sedimentary records, interpret them, and tell you something about the paleo environment and the events that may be laid down the sediments within the rock or sedimentary record. And those folks have spent a long time working on quantitative relationships between the geometry of those deposits, of the cross sets, the thicknesses, all of those different parameters that sedimentologists would look at, the cross sets within the deposits, the way in which sediments are laid down, and try and understand from laboratory modeling or going out into modern systems, try to understand that process to sedimentary product relationship. However, almost all of the existing theory here ignores hydrological variability, particularly flood magnitude or flood duration, and the importance that has in terms of the morphodynamics and the bed form geometry and the bar geometries that are deposited within that record. And of course, they're the things that control the stratigraphy of the deposit. So going back to the system here, where we know we've got these morphodynamics, but we can use this framework. We can use the understanding both from Earth observation and the H-star model to test some of these things. We've got the tools to do this now. So what I'll present to you here now is, it was published a few years ago in Geology, a paper led by Andrew Nicholas within the broader team. And I'm going to show you a set of simulations based on the prototype river of the Rio Paraná in Argentina. We characterized the deposits of the modern Paraná using ground penetrating radar to look at the layers of the stratigraphy, and we looked at a range of sediment cores as well, up to about 5 meters in length, so big suction cores through the sandbars. We ran the hydrological regime, the flood hydrographs, where we varied from 10,000 cumecs to 30,000 cumecs at peak, and we ran the duration of the floods around 175 flood events. We ran simulations where the floods with a hydrograph duration was increased, so how long the flood lasted was increased and changed between between the events. We had a steady discharge, and then we had a much longer duration flood event. And this is just to give you some of the examples. This is the modern Paraná. This is the model that we used, and we simulated the deposits from the model. So we built up the stratigraphy in the model, and then we were able to quantify the erosion surfaces. We were able to quantify the types of deposits, so slack water deposits, so ripples and mud drape areas. So that the model was predicting slow velocities during deposition in these locations. Erosional surfaces, where we had new kind of reactivation surfaces within the sedimentary deposits, and then the green lines here are where we were predicting, dune deposits, so bed sets produced by dunes, and we can look at and compare the model, the real Paraná, and look at the sorts of behaviours between the two, and satisfy ourselves that the model was producing something similar to the modern Paraná with a setup using a set of parameters that mapped to the Paraná. What's really interesting when we start delving into the deposits here is the difference between having a constant discharge and then having a variable discharge. And you can see that from the probability density functions. So I'll draw your attention to panel B, where we have a variable discharge or a constant discharge, how you get very different scales of scour and fill in terms of the deposits that you see. So you have this much more dynamic morphodynamics as a result of the changing discharge. And when we look at the mean set thickness and over the flow depth, you get this departure between the steady discharge, the constant discharge, which have much thicker sets over a much lower portion of the flow depth than you do with the variable discharge runs, where you see this spread out much more through a deeper section of the deposit. So you get very different signatures within the sedimentary record compared to that where you have steady discharge. So the set thickness is related here, and its position in the vertical is related to whether or not you have constant or variable discharge within your model run. So the results demonstrate that the hydrological regime absolutely does influence both the morphodynamics and the sedimentary record in terms of the bar set thickness. Planform morphology on its own is unable to allow you to interpret the variability or the discharge regime of the system, and that was a really important finding. Rivers obviously evolve under these contrasting hydrological regimes, and different rivers with very different hydrological regimes can actually have very similar sedimentary sequences as a result. But you would see that coming through in terms of would have very similar morphologies, but end up with very different sedimentologies. So a decoupling of the produced by the morphodynamics of the system. So variability in the morphodynamics absolutely matters when you're transitioning from morphology to stratigraphy. And of course, that points to a whole range of limitations to many of our established theories of reconstructing paleo flood records from these systems. So that was some of the earlier work that really pointed to the impact of morphodynamics on the way in which floods were recorded within the sedimentary record. Some more recent work that's been led by Chris Skinner here at the University of Hull has started to look at the impact of sediment transport during flood events and how important that can be. This was Storm Desmond in the UK. It devastated a whole range of small villages in an isolated area of Cumbria in the Lake District in the UK, and you can see this river system coming through this small village here. You can see this big overbank fan deposit coming out of the river here. The lake that the river drains to is up here on the right, and you can see this overbank deposit and the calibre of some of the material that was transported by this river. This is the street through the middle of the village, where you could see, some of the material that was cascaded down by the river system. And this is the local post office within the village, and the impact that this had on the village itself. This is a few days later, after some excavators had kind of put the river back into the riverbed because of the deposits, and you can see the amount of material that was needed to be moved to do that. So what we were doing here is reconstructing that flood event to try and understand the drivers of the flood event. And we were using the Caesar list flood model to do this, reconstructing the rainfall into the basin, and then reconstructing the flood event from that. So this is the small catchment, and then we ran two models. I'm going to show you very simply, one with sediment within the model, and one without sediment, so without any sediment transport. So what difference did including sediment within event sediment transport have on these results? And actually, what it showed was that the channel conveyance capacity, so the elevation of the river, when we have sediment conveyed by the river here, we have nearly 50% of peak flood volume increase. So an extra 50% of the peak flood volume came up. Essentially, at the base of the catchment through the village, the river was a metre higher than it would have been without sediment transport aggrading the bed during the event. So this big wave of sediment that moved through the village was one of the key drivers of the big overbank and outer bank action of the river. And you can see here, this is time step in the model, total flow volume on the left, and you can see the impact that this had in terms of elevating the amount of overbank flow that resulted. The final thing I want to talk about today, very briefly, is to try and think about, well, that's great. We're trying to understand variability in flow, understand variability in sediment discharge, even during flood events. But what about vegetation? And this is a big project, a HydroLab project, EU-funded project that Stuart McClelland here in Hull has led for a number of years. And we're trying to understand the role that the vegetation plays in terms of variability and the impact that has on flooding. The other thing we were really interested in trying to do was trying to think about how we scale biology within flume experiments. So Michael Tal at SAFL a few years ago now did some really pioneering work that showed how important vegetation could be for channel pattern and morphodynamics, and Tom Coulthard and others have kind of followed up some of that work. But what we were trying to do here is really think about, well, how do we capture some of these morphodynamics, and how do we then scale the vegetation? Because we can scale model river systems, and we've done that, scale hydrographs, so we can do the scaling of hydrographs, but you're limited with the biology on the time scales that you can simulate, because you're waiting for the biology to respond, and you have a growth cycle that you can't speed up. That's you have very fixed growth rates of vegetation. It's very tricky to do these experiments and change the growth rate of different plants. They've got some variability with species, but then there's all sorts of complicating factors. So we really wanted to test the envelope on some of these things, and really kind of link together fluvial systems, flume experiments, with some very small scale experiments. I'll show you a few of those to finish off with, which are really exciting pieces of work. And then what I would really want to do is then kind of talk about how we might move forward with this as something to finish, where we can use surrogate vegetation and different ways of representing vegetation. And ultimately, what we're trying to do here is look at how we time scale different simulations. And what we have here is different forcing over time, but vegetation growth cycles and recovery really limit what we can do with looking at, if we're looking at climate change impacts on river systems and we're trying to model that in the lab. Scaling that time with vegetation growth rates is really, really tricky. So this is some of the work that Bas Borges did as part of his PhD here in Hull, and we were looking at the way in which we could actually capture the impacts of vegetation here. So this is just some alfalfa seeds we were growing, but actually representing the cohesion that alfalfa produced by putting EPS or xanthan gum in the sediment mix to try and replicate the impact of the cohesion with something that we could actually control within the experiment. So we can actually turn on and off the cohesivity by changing the pH of the water, for example, which allows us to change the timescales of vegetation cohesion within the experiment. It's really exciting in terms of what we're trying to do. So these are based on the Fredericking experiments from 1945, 6, 7, something like that, and with a 45-degree bend, very small scale experiments. And we did this with vegetation, different densities, different types of polymer that are used to act as cohesion. And you can see the different ways in which we represented these, different types, different seeding densities, different amounts of extracellular polymeric substances, so catechine and xanthan gum as those polymers, different weight percentages of those to act as different cohesions. And you can see the sorts of effects that the vegetation density has on the speed of bank retreat, so the cohesive effects. We can grow them for different lengths of time as well as densities, and look at the relative impact of vegetation density against vegetation age, for example, with bank retreat rates in a set of experiments. And what we were able to do is obviously automate all of this stuff through repeat runs, and then be able to look at the speed. And this is one where we have xanthan gum within the experiment, and you can see the sorts of time scales we're able to run over, and we can try to replicate the vegetation effects using these cohesive impacts. And then of course we can start playing with different mixtures, and the rates of retreat. So these are surface areas. So the black is basically a surface area retreating much more quickly than the blue here, and we can measure all of these retreat rates as a result. And then we can start to replicate some of these using the EPS, using the synthetic cohesion within the experiments, and start to map across vegetation type and cohesion with the equivalent synthetic vegetation using the EPS. And we can start looking at the different types of cohesive effects that we have, different types of vegetation, and start playing with some of these things so we can get the representation right within the results. And then what we can then do is take that to a much bigger scale into our total environment simulator and run some really big experiments where we start looking at some of the impacts of vegetation on morphodynamics and then flood conveyance as a result. So these are some of the experimental runs that Rocio Fernandez did, looking at different scales of flood events with different types of vegetation and different synthetic vegetations as well. And we're able to start scaling some of these relationships and the impacts it has on the morphodynamics as well. Oops. One second, sorry. It's just struggling here. Just to say, yeah, we of course quantified all of the experiments with photogrammetry, total terrestrial laser scans, monitoring sediment discharge, monitoring water discharge as well through the experiments, and we did a whole range of different types of controls, large floods, small floods, and scaled all the different floods as a result of that. So just to mention here. And of course, what we were then also able to do is seed different ages of vegetation as well. So we have a whole range of experiments that we're working through at the moment, where we were able to demonstrate the impact of the vegetation on the morphodynamics and the morphodynamics on the flood conveyance as well. And of course, the summary, the quick conclusions here, just as I wrap up, is that vegetation age was shown to be really important. And that means that the event sequencing becomes really important as well, because if you start changing the frequency of significant flood events in terms of hydroclimate, you don't have the recovery time for the vegetation to recover between events that you perhaps had in the past. So that change in frequency of flood events really does begin to impact on the vegetation, and frequency is more important than magnitude of the flood events in terms of vegetation recovery. We're able to show how different types of vegetation at different ages were able to protect banks in different ways. Even in these scaled experiments, that came through as a really important set of parameters. So the older the vegetation was, the more protection it provided to the banks, and the more it slowed down the bank retreat rates. Using EPS is the results are very sensitive, and the effectiveness of the different types of EPS varies, but it provides us with a platform, and we've shown this, to be able to test a whole range of different scenarios. So we're able to kind of change timescales in the experiments far more easily than we could with just vegetation alone. And one of the exciting things is that Cartesian in itself is pH sensitive in terms of its cohesion. So if we change the pH of the water in the flume, we're able to turn cohesivity off and on, which is really exciting in terms of what we might be able to do with time scales and representing vegetation in longer term experiments, where we can, without changing the sediment, without seeding different vegetations, we can change cohesion dynamically through time, through that change in pH. So some closing thoughts. Variability absolutely matters, particularly in terms of its impact on morphodynamics, and becomes more and more important when we start thinking about coupling morphology to sedimentology, and then the impact of vegetation has on those timescales as well. Flow variability matters more for sedimentology, but frequency matters more for the frequency of the floods. The gaps between the floods matters more for vegetation and its impacts. There's a whole range of impacts in terms of understanding how changing flood hazard and risk are incorporated within interpretations of the rock record. I think we're only beginning to scratch the surface on some of those relationships, which are incredibly important for recovering those timescales. Sediment transport, particularly during flood events, is more important than perhaps we thought, particularly in perhaps an end member may be, but incredibly important in the example that I showed you from Storm Desmond. And we, at the moment, all of our flood models don't incorporate any of those dynamic changes within event timescales. Overall, variability in cohesion and vegetation timescales will be really important when we start to think about how biotic and abiotic systems interact and how rivers respond to climate change. We can't ignore the impact on vegetation and on biology when we're thinking about how rivers are going to adjust in response to changing climate. So with that, I'll stop talking. Hopefully, kept most of you interested as I've walked through the presentation, and I look forward to any questions that you may have. So thanks again, and thanks very much for the invitation once more.
Thank you, Dr. Person, for giving us such a very interesting keynote lecture. Dr. Abad will help us with the next part of the event regarding the questions and answers. Por favor, Dr. Abad, ¿nos podría ayudar con esta parte?
Sí, gracias, Daniel. Dan, thank you so much. It was very, very interesting and clear. You know, your vision that flooding is happening around the world, and also the importance of morphology and morphodynamics and developing these, you know, numerical models and combining with experiments and field work. And, you know, we have some questions here. I am going to go through the Facebook web, and also there are some questions here.
Sure.
So Cesar Espiritu, he asks, you know, what is the minimum scale of a basin, you know, the river long and the range of time to obtain an adequate model?
Yeah, so within the, I think this is within the Evo flood model. So we think we'll be simulating down to about 100 square kilometers of river basin within the global flood model. So something of that order. So we won't capture basins of that sort of scale, but anything bigger than that we will be capturing explicitly within the modeling domain. Of course, some of the work is also with Earth observation will be limited to both Sentinel now, I guess, and some planet work as well. So there's some resolution things there and getting into the very small channels. But of course, as we go back in time and we're interested in the evolution of river channels here, we get into the impacts of Landsat and the resolutions that Landsat give us. Again, means that we'll be biased to the bigger rivers and the bigger basins for the longer records. But that's where we'll be obviously coupling this with some of the morphodynamic modeling, what we could do at smaller scales. But yeah, around 100 square kilometers, something of that order.
Perfect, Dan. Thank you. Lucas from Argentina, he asks, in order to calibrate these sedimentological models to represent flooding, it's very difficult to this calibration. And how do you do calibrate on high flows? Because it's very difficult to measure. How?
Yeah, absolutely. That's a great question. So the experiments that we did within the Paraná were obviously based on ground penetrating radar and sediment cores, some of which we know were deposited during the major 1983 flood event. So we've got some baseline information that allows us to kind of couple and understand those those elements. So we were absolutely able to kind of detail and understand those. And then what we were able to then also do is link that together with the kind of measurements we were able to take from the modeling as well, so that we can absolutely kind of begin to map some of those parameters across. Now of course on some of this we won't be capturing the biggest, largest scale flood events, but we will understand as a result of that the range where we're able to capture some of those I guess comparisons, and some of it will be beyond, we haven't seen the 1 in 1,000-year flood event, for example. So we get behaviors, we understand some of the behaviors of the model, we're able to map to some of the major flood events we've seen over recent times, but we're not able to really link all of that together fully through time and space, if that makes sense.
Yeah, thank you, Dan. I do have a question. Jorge Quispe also asked a question, but I'm going to modify it, including to the other question that I have. You show the flooding in Taiwan, which you have to, you put, I think, a riverbed degradation of 3 meters, and then you have more people affected by flooding. And in Peru, we do have every year we have flooding and also sediment transport deposition, and then morphology raises the bed level, and then you have more flooding, even though the discharge is not the highest. So, and in Peru, engineers, they propose every year to dredge the river, So what is this engineering solution in Taiwan? How do they are going to reduce the risks into the population?
Yeah, they do exactly the same in Taiwan. So when you've got the gradient, right, it makes sense to dredge the system. We've had some floods here in the UK, and particularly on some lowland coastal plains, incredibly lowland coastal plains, where the dredging doesn't help you at all with your energy slope. And of course, the general population, like, you have to dredge the rivers, and you're kind of there going, well, the only thing you'll do if you dredge the rivers here is increase the tidal prism have more tidal flood risk. So there's a balance depending on the system. In much of eastern Taiwan, they do the same thing. They dredge the system because they've got the energy slope, the gradient to get the water through. But it clearly, as shown with the Storm Desmond example, you can't dredge during a big flood event, and some of the sediment transport that you see actually during the flood event it can be really important as well. So yeah, I mean, in some areas, and this is kind of what we'll test out, is it's you have some areas where you have this long-term evolving bed aggradation over time that's really hard to kind of pick up unless you're looking for it. And some of Louise Slater's work shown people are thinking it's hydroclimate driving some of this. It's actually morphodynamics changing that's causing some of this. Whereas in other areas, if you have a really big extreme event like Typhoon Morakot, you can actually visibly see some of Janet Hook's work as shown this in southeast Spain as well, where you can actually see some of these rapid aggradations of the bed. The management solution I think is as you've said is the dredging, the removal of that material. But that's likely to get more and more costly over time. But if that's a balance that we need to do through our river engineering works, etc. And then finally, of course, in Peru, with some of the work that we've been doing is really thinking about, well, how does changing sediment regime impact this as well? So with retreating glacial ice, or in other parts of the world where you have some of the work in the Mekong we've been doing, where you're getting changing land use, you have very different sediment supply regimes into the future as well. So it's not just climate change that's impacting a lot of this. It's the kind of onward impacts of either economic development and or climate change impacts over other parts of the basin through land use change or retreating ice that is then changing the sediment regime of the system as well. So, and not accounting for that in the way in which we model flooding, I think is going to be a big limitation for us, and one that I think we need to address going forward.
Yeah, and also infrastructure. In Peru, we do have hydropower dams in the Marañón River that are planned, like 20 dams that will stop sediment for transporting downstream. So
absolutely right. And in some of the other work we're doing in the Mekong is really highlighting the impact of sand mining and other river management pieces, where again, you've got to counter the impacts of some of this dredging, sand mining versus the impact of changing tidal regime as well with sea level rise. So there's lots in terms of balancing out these different factors and how they can combine to really generate changing flood hazard and risk. And finally, Jorge, I think some of the things that Tom Coulthard and others here in Hull have been looking at is kind of looking at combination flood hazards. I didn't really have time to go into that today, but one of the second on the UK National Risk Register, so the government's National Risk Register, the second biggest risk behind global pandemics, I have to say, is tidal flooding from the North Sea. And one of the things that has given many people cause for concern, and this is why there's a big piece of work going on to understand it, is the possibilities of having combination flooding. So when the rivers are in flood, you have a tidal surge at the same time. So maybe it's a 1 in 50 year river flood and a 1 in 50 year tidal surge, and then all of a sudden you have a 1 in 1,000 year flood event. So these kind of black swan flood events, as we call them, where you have a combination of relatively not that extreme flood events, really. They're relatively kind of probable to happen in our lifetimes, but because they're going to happen at the same time, you get this massive event as a result, and you only have to look at the impact of extremes where we've not planned our infrastructure for those extremes, like Fukushima, for example, to begin to think about, well, if we do get these combinations of hazards happening at the same time, then how vulnerable is some of our critical infrastructure, like nuclear power stations, for example, to some of these events? And yeah, there's a lot of work going into some of that as well at the moment. And infrastructure and its management in terms of climate is going to be important.
That's going to be the future, I think, balance between infrastructure development, cities, and then how to understand nature and in general. So just the last question. I know it's very late in UK, and I have a question. Jorge Quispe, he asks, in terms to evaluate flooding, what are the main parameters to consider? And I will add a little bit, and you mentioned a lot in your talk, sediment transport, morphology, and in this part of the world, at least in South America, agencies do not measure much sediment transport and morphology. I mean, a few for different, let's say, purposes, but in general, to understand rivers, not yet at the level maybe as the Mekong or other parts of the world. So what are your thoughts on that?
Yeah, so in many parts of the world, where you do have measurements. I mean, there are lots of parts of the world where we still don't have very many measurements at all, and indeed lots of the monitoring campaigns, when you start looking at it, I've actually withdrawn back a little bit in terms of being able to have, the number of hydrographic stations, I think, was at a maximum in the 1970s, and all over the world, even in the US, the number of USGS stations has declined as well. So the amount of monitoring that's happening is retreating. So there are lots of parts that are ungauged, and we just have some very basic models of those systems. Where we do have measurements, there are a lot of measurements that are water level only, so we don't have discharge, and we have to rely on stage discharge relationships that are sporadically qualities variable on those too. There are obviously a range of really good measurements where we've got stage discharge and or some velocity measurements, which are regularly obtained, which are fantastic, and of course that gives you at the same time, and many of the ways in which these are collected now with hydroacoustics gives you a synoptic picture, but also allows you to know the width and depth and the shape of the channel, which is great. And that's what Louise Slater's work's done, is use those data sets to look at changes in width and depth. We're using those data, and yeah, sediment transport is even less monitored. So I think you ask somebody what the sediment discharge of some of the global rivers, they'll go to Milliman Savitsky, and it's kind of 2 megatons plus or minus 2 megatons, right? and that's the measurements we've got. So there's a push to kind of look, try and improve that from two ways, and I'll finish on these because I think it's a really exciting area. The first way is to look at MVDI or multispectral returns from satellite imagery, and try to recover suspended sediment concentrations from Earth observation data sets. And I think that holds a range of really interesting promise for the future. Tied to that is kind of using really super high resolution kind of planet type satellite work to maybe even start looking at surface discharges as well, or surface velocities from some of those technologies, which is really super interesting as well. And then finally, I think using what records where we do have ADCP records or hydroacoustic measures is actually using the acoustic backscatter, and this is what we did in the Mekong, was using legacy data. So these systems monitor, they obtain the acoustic backscatter, and hydrographic agencies tend to file these away in big data stores, right? And what we've been doing is going and calibrating as many of these instruments as we can, so that we can actually recover suspended sediment concentration from these historic data sets. We already have the flow discharge, if we can calibrate those instruments, then we're able to recover the sediment discharge as well. There's a lot of work involved, a lot of assumptions. These instruments have been designed to recover the Doppler shift, so the acoustics they're not great acoustics on these things. They're not calibrated very well, so there's a lot of work to do in that space, but there is potentially a very long-term record of hydroacoustic measurements with sediment discharges within them. We've got a key to go and kind of unlock it, but we can go and recover those data sets and look at how sediment discharge has changed over time, which is really exciting.
Bueno, con esta última pregunta damos por finalizada la ponencia. Sin embargo, quisiera aprovechar en dar muchas gracias al Dr. Parsons. Thank you, Dr. Parsons. Hope we can have you here soon in Peru. You can visit us.
I'd love to visit. Yeah, I'd have been there already if it wasn't for COVID. But yeah, I'm very much looking forward to coming to visit.
Sure, so we can give us a lecture in person, maybe.
Yeah, no, that'd be fantastic.
Y también queremos agradecer a los coorganizadores, a las 3 universidades, a la Universidad Nacional Elminio Valdizán de Huánuco, a la Universidad Nacional de la Amazonía Peruana de Iquitos, Loreto, y también a la Universidad Nacional San Antonio Abad del Cusco, por coorganizar este tan interesante evento. Agradecemos el tiempo que ha dedicado el Dr. Parsons en compartir sus experiencias, esperamos tenerlo pronto. Nuevamente, muchas gracias a todos los que nos siguieron la transmisión vía Zoom y también en nuestras redes sociales. Como se indicó previamente, estaremos sorteando 2 medias becas al curso virtual que se dará inicio este próximo 31 de mayo, que se titula Modelamiento hidrodinámico, transporte de sedimentos y morfología de fondo para ríos. Recuerden visitar la página del Facebook donde publicaremos próximamente los resultados. Asimismo, mencionamos para quienes desean volver a ver la charla o conocer un poco más sobre el tema, este evento quedará grabado en nuestro canal de YouTube. Los esperamos entonces en la siguiente serie de webinars que se dará inicio el 23 de junio del presente año. Tendrá por título Experiencias de mediciones hidroacústicas en ríos, desde protocolos y validación hacia las mejores prácticas. Tendremos la participación de 3 importantes investigadores en el área de modelamiento y mediciones en campo en hidráulica del Servicio Geológico de los Estados Unidos, de la Universidad Nacional de Córdoba, Argentina, y también de la Universidad Nacional del Litoral. Los esperamos. Las inscripciones estarán disponibles en nuestra página de Facebook. Muchas gracias a todos.
Thank you, Dan.
Bye, everybody.
Nice to see you.
Take care, folks. Bye.
Bye-bye. Thank you.